Hi, my name is Francesco Laccone from the ISTI-CNR in Pisa, and my contribution is entitled Constrained Shape Optimization of Grid Shells Based on Deep Learning. In this presentation, I'm going to show you a new method for shape optimization that improves the structural performances that are the color map in this animation and the sustainability of grid shells, trying to preserve the main geometric features as much as possible. Grid shells are architectural structures whose geometry is based on a mesh and in which the edges define the load-bearing beams. This method uses neural networks and merges knowledge from statics and differential geometry. We consider grid shells encoded as meshes and a vector of geometric features. The learning model predicts the translation vectors that are displacement to be applied at the nodes of grid shells, and at each intermediate step we compute a loss function until convergence. We developed a single instance paradigm in which we solve this problem, such as find the optimal mesh through a neural network such that the optimal weights are those that minimize a loss function. Single instance paradigm means that for each mesh we restart the weights and we reset a new gradient descent procedure. The input grid shell is a triangular mesh made of vertices, edges, and faces. We use the network of edges to compute the loss function, as I will show in the next slide, while we use the vertices and faces to compute the geometric features that are extrinsic features such as vertex coordinates, normals, and principal curvature, and intrinsic features such as geodesic and distance and centrality measures. Our neural network is basically made of three components: an encoder, an attention layers, and reduct function. We start from the vertex of feature vectors. The encoder maps transforms the input features clusters into a vector in range -1, 1. Then these encoded features are fed into a sequence of 4 graph attention layers, and here we work on feature space, and for each point the weights are learned as weighted average. And the reduct function takes as output this information and predicts the displacement. Other details are in the computers and structures paper. The loss function is the sum of 3 components. The first one is the structural, that is basically the average strain energy on the beams. And what is relevant here is the very simple and effective implementation that allows us to obtain a differentiable strain energy with respect to the vertex coordinates, so that we can exploit the PyTorch automatic differentiation in our neural network. To preserve the fairness of the boundaries, we include a second term b, which is a penalty function that ensures that the displacement at the fixed degrees of freedom are small during the learning, and thus we can avoid the formation of wrinkles around the boundaries. Last component is inspired by the free grid benchmark that promotes an holistic performance assessment of grid shells based on 3 components: structural, buildability, and sustainability. In particular, the last one minimizes the carbon emissions of grid shells by reducing the sum of the total beam lengths. In this slide you can observe some results. You have starting and final performances for 2 examples, and in this histogram you have normalized performance of the main relevant components of the loss. We can see that the structural component tries to alter the shape towards low bending solutions. For instance, you can see that there is an increase of curvature in the flatter areas, while the sustainability is acting as a brake and limits the elongation of the beams. So as in classic multi-objective optimization, the performances are usually quite conflicting, but overall you can observe that the shapes look quite similar to the original. So to conclude, we found that these results are very interesting, and we are working on several directions to expand the capabilities of these methods. The QR code points to our repository where you can find other details, examples, and results. Thank you.